So the story of Euclid's 5 axioms is incredibly famous at this point. You have the first 4, which define the laws of neutral geometry, and then you have a strange 5th axiom, which looks nothing like the rest. This 5th axiom is often known as the parallel postulate. And you'll often hear this trichotomy where there are essentially 3 different worlds that neutral geometry can hold in. If the parallel postulate holds, you have planar geometry with exactly 1 parallel line for each point. If there are 0 parallel lines, you have spherical geometry. And if you have more than 1 parallel line, you have hyperbolic geometry. Now, the dichotomy between planar geometry and hyperbolic geometry is golden. With spherical geometry, the comparison is misleading. The reason that spherical geometry has 0 parallel lines isn't because parallel postulate doesn't hold. It's because it's not a neutral geometry system at all. In fact, it's not too much of a stretch to say that the parallel postulate actually does hold in spherical geometry. Let's look back at Euclid's 5 axioms, focusing in on the first 4. For planes and hyperbolic spaces, these are all satisfied, and thus we can consider them neutral or absolute geometries. For spheres, some of these statements are complete nonsense. Any straight line segment can be extended indefinitely in a straight line. That's certainly not true in spheres. You can extend the notion by saying that spheres have unbounded circles, but not indefinite ones. They don't stretch on forever. There's other red flags when applying these axioms to spherical geometry, but axiom 2 is the one that really matters in our case. To see why, let's dive deeper into the parallel postulate. First, the parallel postulate doesn't actually say that you have exactly 1 line through the point parallel to another line. It says that you have at most 1. So this reformulation of Euclid's 5th axiom is called Playfair's axiom, and it's equivalent to Euclid's 5th axiom in neutral geometry systems. The reason why is because we can actually get the other half using the first 4 axioms. We can guarantee at least 1 using the first 4 axiom, and Playfair bounds it by 1. Thus, we have exactly 1 without having to invoke that specifically in Playfair's axiom. If Playfair said exactly 1, that'd be redundant in an axiom system, and redundancy is not something that we want. So with Playfair's axiom, we can see that spherical geometry actually does satisfy it. 0 parallel line satisfies the at most 1 condition. So what went wrong here? If Playfair's axiom is equivalent to the parallel postulate, how come Playfair's axiom holds in spherical geometry when the parallel postulate is clearly false? Or is it? The reason is we need to look at the first 4 axioms of Euclid to even make sense of the 5th. Let's see how the first 4 axioms prove the at least 1 condition first. First, we have a line and a point that is not on the line. Then, using proposition 1.12 of Euclid, we can construct a perpendicular line to the point. Using 1.11, we can construct a perpendicular of the perpendicular. We can do the same construction in spherical geometry, so that's not our issue here. Next, Euclid argues using proposition 1.27. This states that alternate interior angles congruent implies parallel lines. To prove this, we use a contradiction argument. Let's assume that the lines are not parallel, and we have alternate interior angles congruent. If we extend these lines, we'll eventually find a meeting point. That's just the definition of it not being parallel. With this meeting point, we can use the exterior angle theorem. No, not that one. It's a weaker version that still holds in neutral geometry. However, if we look at the proof of the exterior angle theorem, it again involves axiom 2, extending lines. Euclid assumes that we can extend a line to double its length. And if we double its length, that leaves it outside of the triangle, and we can make a bunch of constructions. But on a sphere, if we double a line's length, it can end up back inside the triangle because we have that wrapping around. Thus, such an argument doesn't hold, and the exterior angle theorem is false. Thus, we have reached the failure of spherical geometry. We can't have parallel lines, not because the 5th axiom isn't true, because the first 4 don't. Because the first 4 axioms aren't true, we aren't guaranteed the at least 1 parallel line. Alright, one final tangent. Let's look specifically at Euclid's 5th axiom using the wording that he wrote it with. If a straight line intersects 2 other straight lines, forming 2 interior angles on the same side that are less than 2 right angles, and the 2 lines, if extended indefinitely, meet on that side in which the angles sum to less than 2 right angles. Well, we can't really say that this is false for spherical geometry either, because we don't really have a notion of what the same side is on spherical geometry. Euclid's axioms and definitions are really ill-defined and are not really good benchmarks of an axiomatic system in modern geometry. Instead, we can use a much more complete axiom system like Hilbert or Tarski. Let's look at Hilbert's. This system doesn't actually define what anything is, but rather uses relations to show properties of the objects. This is a much better system than saying something like a line is that which has no breadth, because what does that even mean? Some of these relations that are used to define the objects are incidence, congruence, and betweenness. But wait a minute. On spherical geometry, what does it mean for something to be in between two other points? Thus, we shouldn't really be surprised that spherical geometry isn't a neutral geometry system when the basic relation of betweenness is ill-defined. We can't even say that a point is in between two other points. So to recap, the fifth axiom, when taking out all the bloat, doesn't give exactly one parallel. It gives at most one parallel. This is because in neutral geometries, the four axioms give us at least one parallel line. Spherical geometry has zero because it's not in the same category, not because of the parallel postulate. In fact, if you consider Playfair's axiom, it does hold. If you consider Euclid's fifth axiom, it's ill-defined, so I guess we could call that vacuously true. And if you consider Hilbert's formulation of the parallel postulate, it's also equivalent to Playfair's axiom. So in fact, parallel postulate does hold in spherical geometry.